Good morning. Thanks all of you for being here. First order of business, can you hear me? Okay. Second, too loud? Louder. I'll shout. I'm good. Second order of business is, despite heroic efforts by the staff here, this screen does not seem to be working because the projector refuses to turn on. There are about 20 seats still remaining over here, so I would suggest everybody start shifting this way, fill in all the spots, and get as far this way as we can. I think then everyone will be able to see the screen reasonably well. We still have about, if you guys are happy over there, I'm happy. But there are about 10 more seats over here. If you can't see the screen, you might want to move a little bit further over. Last chance. It's like being a flight attendant. We have one in the middle here. I know you prefer the aisles. All right, we're going to do one more experiment to figure out how this room will work best for us. Well, we need to do an experiment with the lights. I don't want you to all go to sleep. But it's awfully bright on here, so maybe we could, can we see if we can turn off, it'd be nice if we're just the front lights or the left lights. Maybe we can leave these on and turn these off. There we are. All right. Welcome to the 21st century. We're good. All right. So that you know what you're getting in for, I think you had a handout. You read something on the website or somewhere else about what this class is about. We'll be here for 6 weeks. The subject is this question, how old is the universe? And as you heard, I wrote the book on it, so I know a little bit about it. For those of you, this isn't a sales pitch, it's just informational. For those of you who decide that you want to know a bit more about the subject beyond what we'll actually do in 6 hours or so over the next 6 weeks, the bookstore will be here after class if you want to get a copy of the book. You certainly don't need to. If you decide after a couple sessions, yeah, you really like the book, they're going to come back in the 3rd week so that you don't have to go trudging around town because there are no bookstores left, right? So if you want the book, we've got to bring the mountain to you, okay? But again, it's up to you whether you want it. I'll see if I can inspire you today to want to.
Is it on Amazon yet?
It's on Amazon, yes.
How much is?
Less on Amazon than anywhere else. I don't know what the price is. Not quite. Okay? I'll say something about that. That's a fair question. I'm going to use it as a textbook, but no one else is.
We'll buy it if you will sign it.
I'd be happy to sign it. Let me answer the textbook question. Tell you how this began. I do teach a course just about every year that's an Introduction to Astronomy course here at Vanderbilt. It's Astronomy 102. And over the years, I got very frustrated with the standard textbook, which cost the students $150. And it's an encyclopedia that covers everything in astronomy and does nothing well. It's designed so that every professor at every university in the country can find that little piece in the book. And then the students are quite mad because they haven't used 38 of the 47 chapters and they paid $150 for it. But I also came away from the experience being convinced that the students didn't learn anything, because it was an exercise in learning trivia rather than learning something perhaps important. So I spent a lot of years thinking about what that course should be about, and I decided that in any presentation, if I'm lucky, you will leave here remembering one thing. I'm really lucky too. Okay? But one thing from any talk. Whether it's a 5-minute talk, a 1-hour talk, or 6 weeks. You'll remember one thing. I don't know what that one thing is going to be, but I decided that that introductory course should be about this question. That I want students to understand how astronomers have decided that we actually know how to answer this question. They don't have to agree with the answer, but I want them to understand what astronomers do in coming up with the answer. So when the book finally came out, and I do have a copy here somewhere, looks like this. It arrived in March on my doorstep, and my wife opened it up, and she read the dust jacket, and she said, "Oh, astronomers have determined that the universe is 13.7 billion years old." You gave away the answer. Why did you do that? It's not a mystery novel. Okay? I'm not Jason Bourne. Okay? The goal is to get my readers to understand why we think that's the right answer. And astronomers are pretty convinced we know that that's the right answer. And that's a pretty amazing thing that we can do that. So this actually began as a textbook, or an attempt to build a textbook. And it had lots of math and lots of physics in it, and lots of homework problems. And it was for my class. Once I did that, I decided that maybe some other people would be interested in this, but not with the math, not with the homework problems. So I actually excised the college physics from the book and left in the book the story. So my students next year will actually use the book, but they will have a website that also has, for chapter 1, here's the math, here's the physics, here are the homework problems, here are the questions, for chapter 2, etc. But none of that's in the book. If you want to access the website, I could give it to you if you really want to do the homework. But the book is a story, and it's fairly readable, I think. You can go to Amazon.com and find lots of reviews and other things. I think it works for you, for the general reader. But I'm not the general reader, so you'll have to decide whether I've succeeded or not. So let me get started. The first week today is really going to be some history on why this is even a question worth asking. Next week, we're going to talk about some basic things we astronomers do that we have to be able to do in order to try to answer this question. These are really the tools of the trade, but I want you to be convinced that astronomers actually know what we're doing. We need to be able to measure simple things like how hot stars are, how far away stars are, how fast stars or galaxies are moving, whether that object out there is a star or a galaxy, and what's the difference. So next week is about a bunch of basic things in astronomy that we need in order to have a conversation about this question. And then the last 4 weeks are about 4 different ways in which astronomers have tried to answer this question. That's where we're going. Anybody want to leave? One, you want to leave? All right. So how are we going to answer this question? How old is the universe? If we want to start with the basics, we might start with what we know and ask another question, which is a very simple question, and that is, see if this works. Something didn't work. It's supposed to change words like that. All right. Okay. How old is the Earth? There's a very simple assumption here, and that assumption is the Earth must be younger than the universe since the Earth is part of the universe. If you don't think about it much, you don't go there, but it ought to be true. It's hard to come up with a reason why it wouldn't be true. And perhaps we can figure out the age of the Earth. If we can figure out the age of the Earth, we at least have a starting point for answering the question, how old is the universe? So, how old is the Earth, and how do we know that? Anybody have an answer? How old is the Earth? 4-something billion? Yeah. We'll get there. We'll get there. But let me tell you where we came from, because this is actually what I'm interested in talking to you about today. If you can't read the words on the screen because they've disappeared a little bit, I'll read them to you. Let's go back 3,000 years. And try to understand how humans got into this business of astronomy and of asking this question. So I'm going to go back to Greek mythology, and apparently if I stand there, I'm on that microphone and this microphone, so that's dangerous. In the beginning, there came nothing alone. It was sometimes called chaos, or the void, but it was nothing all the same. Next appeared earth, so the gods would have some place to stand. So how old is the earth? What is this? What answer do you get from this? None. There's not as old as the gods. It's sort of a non-answer. It wasn't a question, but there also wasn't an answer. So let's see if anybody else was any smarter. We'll go to the Marshall Islands. In the beginning, long ago, there was only the ocean. Then the god Loa came down, and he commanded. He caused a humming sound, and the Marshall Islands were made. So how old? So younger than the ocean. Yeah. So we'll go to Tahiti. Ta'aroa lived alone in a shell shaped much like an egg. The egg revolved in a dark, empty space for ages. Then came a new time, and Ta'aroa broke out of the egg. Being so by himself, he made the god Tu. Tu became Ta'aroa's great companion and helper in the wonderful creation. Ta'aroa and Tu made gods to fill every place. They made the universe, and they brought forth land and creatures. So how old is the earth? Older than, well, not as old as Ta'aroa, but there are a lot of egg stories, ancient mythology stories that are based on the egg. Seems like an obvious thing, but it doesn't tell us how old the earth or the universe is. So we'll come back to North America, to the Huron Indians. In the beginning, there was only water, and the water animals that lived in it. Then a woman fell from a torn place in the sky. She was a divine woman, full of power. 2 loons flying over the water saw her falling. They flew under her, close together, making a pillow for her to sit on. A snapping turtle and a toad came to help. The animals decided the woman needed earth to live on. Toad went under the water and nearly died. But when he returned and Turtle looked inside Toad's mouth, he found a little earth. The woman took it and put it all around on Turtle's shell. That was the start of the earth. And that's one of many turtle stories in mythology. And it tells us that the earth is whatever it is, okay? But there was water first, and there were water animals before there was earth. But it doesn't tell us how old the water is either. So we'll go to China. Another egg story. The space of the universe was in the shape of a hen's egg. Within the egg, there was a great mass called No Thing. Inside of No Thing was something not yet born. It was not yet developed, and it was called Fan Ku. In no time, Fan Ku burst from the egg. He was the first being. He was the great creator. Fan Ku was the size of a giant. He grew 10 feet a day and lived for 18,000 years. Hair grew all over Fan Ku. Horns curved up out of his head, and tusks jutted from his jaw. In one hand, he held a chisel, and with it, he carved out the world. And there you have it. 2,500, 3,000 years ago, how old is the universe was not a question. Nobody asked the question. How old is the earth was not a question. It takes a certain level of sophistication to get to the point at which we can think this is a meaningful question. And to ancient peoples all over the world, this was not a question. This changed a little bit in ancient Greece. So we have Aristotle here. Aristotle did most of his work in the 4th century BCE, and Aristotle was very convincing with all his ideas. Aristotle's ideas survived for about 2,000 years. And in physics and astronomy, that's certainly pretty good. If I have any ideas that anybody thinks are any good in astronomy that anyone still believes in 25 years, let alone 2,000 years, I'd be pretty happy. So Aristotle, wherever he is, ought to be pretty happy. Aristotle came up with basic ideas for the physics of the universe. The first person to really do that. And his basic concept of the universe was built on the idea that there were fundamental elements that made up the universe. Those 4 elements were earth, air, fire, water. Students usually tell me wind. Earth, Wind, and Fire? No, that's the group. Okay? Earth, water, fire, and air. The four fundamental elements. Those four elements, let me get something that I won't break. My keys. Those fundamental elements do certain things. So this is made of stuff that Aristotle would say is made of earthy stuff. And if I let go of them, what happens? Broke my clicker, probably. All right. So earthy stuff falls. That's not good enough. Where's it going? To the center of the earth. That's not good enough. It's going somewhere because it has a purpose. And its purpose is to get where it's supposed to go. Okay? It does go down, but down is defined as in a particular direction. That particular direction happens to be toward the center of the earth, but the center of the earth is an even more important place. It is the center of the universe. Earthy materials go toward the center of the universe because that's what they're supposed to do. Everything in the universe, according to Aristotle, has a purpose, telos. And telos for earthy stuff is to go toward the center of the universe, which looks to you and me like down. But down is defined as a very special direction. Water also goes toward the center of the universe, but water is not supposed to get as close to the center of the universe as earthy stuff, so it surrounds the earth. And what do air and fire do? They go up. Not good enough. Where do they go? Away from the center of the universe, because that's what they're supposed to do. And fire should rise higher than air. So if there was nothing to stop earth, air, fire, and water from getting to where they're supposed to go, we would have a sphere of earth surrounded by a sphere of water, surrounded by a sphere of air, surrounded by a sphere of fire. And that's sort of what the earth looks like. It's pretty obvious that Aristotle's right. His intuition, his common sense approach to physics is convincing. My physics teacher in high school told me one thing that I remember. I think that's the end of the sentence. I don't remember anything else from physics in high school. Okay? She said, if you stay in this business, if you become a physicist, remember this. In physics, common sense is stupid. And I remember that. And it is stupid because, can I borrow your piece of paper? Piece of paper and my keys. Aristotle says they will both fall at what rates? Wrong. Newton said that. Okay? Because it's obvious that they fall at different rates. Now, all of you know, I hope, that we actually went to the moon, and astronauts did some experiments on the surface of the moon, and there's a wonderful video of one astronaut holding a rock hammer and a feather, and he drops them, and poof, they fall at the same rate, just like Isaac Newton said. In the absence of the resistance of the air, all things fall at the same rate. But we live on the earth where there's air. And our common experience, our common sense says a piece of paper falls at a different rate than the rock material. So our common sense misleads us. You need to delve deeper into the physics of what's happening to truly understand. Aristotle wasn't able to do that. But he was able to convince everybody, that he was right. And his physics said there's earth, air, fire, and water. They behave in certain ways because they have a purpose. Once you've figured that out, then look around the universe, and you'll discover that there's something else that doesn't behave like the earth, air, fire, and water. Something out there that doesn't go up or down. Any help on what that is? Not magnetism. Planets and stars. You look up into the sky at night, or in the daytime with the sun. Do the stars go up and down? Well, they rise and they set, but what they're really doing is they're going around and around and around forever. As far as Aristotle could tell, and he thought that the Greeks at his time had astronomical records from the Babylonians that extended back millions of years. In fact, they had no astronomical records until Alexander the Great went and conquered that part of the world, which was after Aristotle died. So they really knew nothing about Babylonian astronomy. But they thought that the Babylonians had millions of years of observations. And in all of those observations, they had never seen anything in the heavens change. Now, most of you have a little bit of wear on your tires. So you can think back to when you were 7 years old and you looked up in the sky and you saw the Big Dipper. And then you taught your children to look up in the sky to find the Big Dipper. And now many of you may be teaching your children or grandchildren to look up in the sky and find the Big Dipper. And you know what? It's still the Big Dipper. The stars haven't changed. Every day, the Big Dipper rises and the Big Dipper sets, and it does it again the next day and the next day. And it's been doing it for the entire history of humanity. And as best as we can tell, if we're Aristotle, it's going to be doing it forever into the future. And the stars don't seem to move relative to each other. It's still the Big Dipper. Orion's still Orion. The constellation charts that you looked at 100 years ago, well, none of us did that, but the constellation charts that somebody looked at 100 years ago are still going to be completely valid to use 10,000 years from now. Nothing seems to change in the heavens. And Aristotle decided that there was a fifth element in the universe. And that fifth element he called ether. Ether is the Greek word that means to run always. The stuff in the sky runs always. It just keeps on moving. Never stops. If those stars rise, go across the sky, and set today, and they're going to do it tomorrow, they probably did it yesterday and the day before. And Aristotle asked why, trying to figure this out using the same ideas for the laws of physics that he did for the earth, air, fire, and water. And the basic idea is everything has a purpose. What is the purpose of the ether, the fifth element, the quintessence? The purpose of the ether is to go around in circles, to have circular motion rather than up and down motion. And the ether, being in the heavens, being where everything is changeless, must be perfect. Because everything is trying to get better, to achieve your purpose, to achieve your goal. Whether it's people or carrots or earth, air, fire, and water. And the ether is not changing. The only reason it wouldn't change is if there's no need for it to change. It doesn't need to change because it's perfect. And the proof that it's perfect is that it doesn't change. We now have a nice circular argument for the ether that goes in circles. But it's pretty convincing to Aristotle and to the philosophers who lived at the time of Aristotle and forward. So we have 5 elements in the universe: earth, air, fire, and water, plus the ether. And the ether goes around in circles, and it does that forever. If it changed, it wouldn't be perfect. If it wasn't perfect, it wouldn't go in circles. Circles have no beginning, they have no end, and he thought everything has to go in the same direction in a circle, so there's no, what he called a contrary motion backwards. For earthy stuff going down, there's a contrary motion upwards that could slow it down or stop it. There's no contrary motion to circular motion. Everything in the heavens, according to Aristotle, moves at the constant speed in circles forever. And therefore, the ether must be how old? Eternal. So how old is the earth? Eternal. Why is the earth eternal? Well, stuff that moves in circles has to move in a circle around a center. You can't have a circle if there's no center to the circle. Where's the center to the circle? Right here. The earth is the center, not only of the circular motion of the stars, but of the universe. Obviously, ether moves in circles around the center of the universe. The ether could not move in circles if a center did not exist. The center could perhaps pre-exist the stuff that moves in circles, but the circular motion can't pre-exist the center. But the stuff in circular motion couldn't pre-exist the center because if it could not, let me try again. The center could not exist before the ether, because if the center existed before the ether, what would you have to do with the ether? It's not there yet. What do you have to do? Create it. If you create it, it's changed from non-existence to existence. Therefore, it wasn't perfect. Therefore, it isn't perfect, but it is perfect. Therefore, it must have been there forever. Therefore, everything in the universe has been here forever. The earth is eternal. The heavens are eternal. The logic is impeccably wrong. But it convinced everybody for almost 2,000 years. So Aristotle's physics, the earth, air, fire, water, and ether, that was the physics of the universe until Isaac Newton, the late 17th century. That's a long time. And with his physics comes his cosmology, his description of the physical universe. And his description of the physical universe is this one. We have the earth at the center. We have the spheres of water, fire, and air surrounding it. Then we have the sphere of the moon, Mercury's sphere, the sphere of Venus, the sphere of the sun, the sphere of Mars, the sphere of Jupiter, the sphere of Saturn, and then the celestial spheres. And for Aristotle and anybody who believed in an Aristotelian universe, these aren't just circles. These aren't orbits of planets. These are physical spheres in the heavens. Three-dimensional spheres with a thickness and a size, and that was the universe. And all the spheres, everything from the moon and beyond, is made of ether. Everything down here is earth, air, fire, and water. And there's a boundary. Stuff from down here can't get up there, because if stuff from down here got up to where the ether is, it would have to be ether and move in circular motion. And if it moved in circular motion, it would be perfect. And if it's perfect, it couldn't change. But it just changed. It went from being earthy stuff that moved up and down to ether that goes around. So there's a barrier. Nothing can get from down here to up there. That's Aristotle's universe. And in Aristotle's universe, everything is eternal. Is there a question?
You said nothing could go in between, but I thought that's the perfect, I mean, that was the belief of the church. God is out there, Deus, right? And God, and when you died, they believed you went to heaven out there on that last ground, right?
Good questions. Colby, you hear that question? No. Okay. Question is, isn't out here in the heavens? That's where God is. That's where the angels are. So if you're saved, you go to heaven. So you go from down here to up there. Who came first, Aristotle or the church? Aristotle came first 4 centuries before Christ. And then the fathers of the early Catholic Church spent 400 years fighting about Christianity, because they decided that Christianity should be built on top of ancient philosophy. That in order to compete in the marketplace of religious ideas in the Eastern Mediterranean at the time, Christianity would be a rational religion. That's a new concept. In fact, theology means that. It means the rational approach to religious thought. If you're going to do that, you've got to either say Aristotle's wrong, or you've got to build yourself on top of Aristotle. And for 4 centuries, the early Catholic fathers decided to try to build Catholicism on top of Aristotle. And it didn't work, because Aristotle doesn't let you get to heaven.
That's the first time I've ever
Yeah. They tried Plato. That didn't work either. And eventually, Augustine built Catholicism on Neoplatonism rather than on Platonic thought or Aristotelian thought. And that worked until the 13th century, when Thomas Aquinas came along, and after the Crusades, Western scholars had rediscovered Aristotle. And they discovered that Aristotle was awfully convincing about everything, whether it's medicine, political philosophy, the physics of the universe, the astronomy of the universe, you name it, ethics. Aristotle wins. There were commentaries on Aristotle that went back now 1,500 years, and the medieval scholars said, Aristotle must be right. So Aquinas was able to rebuild Catholicism on top of Aristotle, which is why Galileo got in so much trouble, but that's another course. Yes?
How did Aristotle account for the wobble on the earth, so what's the ether appears not being in the same place all the time?
Aristotle didn't know about the wobble of the earth.
Right.
Okay. The rotation axis of the earth precesses with a period of about 26,000 years, so it's slow. That was discovered 3 centuries after Aristotle by Hipparchus. And he made some really good measurements to get that right. He actually did have 1,000 years of Babylonian records, which enabled him to figure this out. Aristotelian cosmology is this nice, pretty, perfect picture. Everything moves in perfect circles centered on the earth. It's not mathematical. Just after Aristotle, somebody else came along and wrote a book that just about all of you studied, and all of your children and grandchildren studied, and this will go on for a long time. Euclid. Okay? So when you studied geometry, you were studying Euclidean geometry in the same way that Euclid wrote that book in 300 BCE. And after Euclid, ancient astronomy really was invented. This is metaphysics. It's not physics. Okay? And the astronomers who followed Aristotle said, we're interested in looking at Jupiter, knowing exactly where it is today, and predicting where it will be on July 17th, 74 years from now. When will Jupiter get near Saturn? Can we predict that? When will the next eclipse of the moon be? Can we predict that? To do that, you need mathematical models of the motions of the things in the heavens. When you start doing that, you discover that the planets don't seem to move in perfect circles that never change speed around the Earth. You watch the planets and they seem to slow down and actually sometimes go backwards and then speed up again and go forwards again. And it's not because they go backwards and forwards again from our modern perspective. It's because we're all going around the sun and the planets closest to the sun go fast. So if you imagine runners on a track, and you have one runner in lane 2 and one runner in lane 8, and the runner in lane 2 runs faster, they lap the person in lane 8. And when they pass the person in lane 8, it looks like the person in lane 8 is going backwards relative to the background. You can try this in a car. When you're on Interstate 40 and you pass a car in the right lane, if you forget about you moving and you just look at that car, it looks like that car is moving backwards because you passed it. So when they did this, they discovered the planets seemed to do weird things, and they created mathematical devices to try to model the motions of the heavens that wasn't this. So they created things called epicycles, which were circular paths centered on these outer circles. So if you imagine, according to Aristotle, the planet's supposed to move along this circle, what it really does is it goes in a circle around that line, but that line carries it forward. So it does this loop-de-loop all the way around. Those were epicycles. That enabled them to predict the correct path for the sun and the moon, but not for the planets. And then a guy, Ptolemy, came along and created more mathematical devices that truly worked. At least worked well enough to match the measurements they could make 2,000 years ago. And there were serious debates. Are these devices, are the epicycles, is the equant point, are these real? Are they actually in the heavens, or do the heavens look like this? And most people believe that the heavens truly look like Aristotle said, because physics says they must. But the mathematics gives you a different answer, different explanation. They call this saving the appearances. They were saving Aristotle's appearances with being as close to Aristotle as possible, even though it wasn't quite. Yes?
Correct to infer that Aristotle saw the Earth as a sphere, because
Yes.
many years later there was that flat Earth society and the ships going over the edge and so forth.
There actually wasn't. The Greeks knew the earth was round. Aristotle wrote a treatise called On the Heavens, and in that treatise he presents 5 arguments for why the earth is a sphere. One of those arguments is if you're a seafaring people, which the Greeks were, if you watch a boat disappear over the horizon, what actually happens visually to that boat? It goes down. It doesn't just get smaller. On a flat Earth, it would just get smaller until it disappeared. But it actually goes down. The hull disappears before the sail. That can't happen on a flat Earth. So that tells you the Earth has a curved surface of some sort. He knew that when you go north from Greece or south from Greece, you see different stars. If the Earth is flat, then if I'm here and I look up, I see the entire sky. If I'm here and I look up, I see the entire sky. But if the Earth is curved, if I go around the curvature of the Earth and now I'm on this part of the Earth, my sky is that way, I can't see those stars anymore. As you go north, you see different stars. The second proof that the Earth is curved, and they claim spherical because he said it had to be a sphere, so curvature must mean spherical. Third argument he had, I can remember the fifth. What are 3 and 4? We'll skip 3 and 4. You can ask me next week. The fifth argument, just to demonstrate that Aristotle didn't always get everything right, but it was logical. If you went from Greece to the east, you'd get to India. And in India, they have elephants. If you go to the west from Greece, you get to Morocco. And in Morocco, they have elephants. Therefore, Morocco and India are contiguous. So if you go that way, you end up over there, the Earth is round. Didn't quite get that one right. Following Aristotle, following Euclid, one of the Greek astronomers by the name of Eratosthenes actually measured the size of the Earth. He used shadows. All you have to do is put a stick in the ground. That's all you have to do. And you measure at noon the shadow from that stick. And you measure the length of the shadow, and you measure the angle from the tip of the stick to the end of the shadow on the ground. And then you go further north or further south. And they knew which direction was north and south. That's easy to do. And you do the same experiment. And you find a place on the Earth where at noon on June 21st, there's no shadow. Because at noon, the sun is straight overhead. And then you pace off the distance from your stick with no shadow to the stick with a shadow, which might be hundreds of kilometers. And the ratio between the distance you paced off and the circumference of the Earth is the same as the ratio of this angle to 360 degrees. It's very, very simple geometry. And when they did that, they got a radius for the Earth somewhere between 40,000 and 42,000 kilometers, which is exactly right. The Greeks knew the size of the Earth in 200 BCE, and they knew it to within a few percent. Columbus knew that he was not sailing off the edge of the Earth. Columbus thought the Earth was smaller than it was. Why that knowledge had been lost, we don't know, or at least I don't know. But in medieval times, in Renaissance times, all scholars knew the Earth was round. There was just some debate about exactly how big it was. Now, Augustine had some logic that said the Earth was flat, but that was actually inconsistent with Aristotle, and it really didn't carry the day for the next 1,000 years. You know, you can read in the Bible the Earth is spread out like a floor under a tent or something like that. But the Greeks knew the Earth was round. That was not a problem. They knew the size of the Earth. They made measurements of the distance to the moon, the distance to the sun. They were off by a factor of 10 in those distances, but they used basic geometry to actually try to measure the physical size of the universe. They were very good at what they did. And for the size of the Earth and the shape of the Earth, they got that one right. So Aristotle says the Earth is round. Aristotle says we have these spherical shells around the Earth. Aristotle says the Earth is eternal, as are the heavens. And no one's really going to argue with that within the scientific and philosophical communities for 2,000 years. There will be debate. There are other arguments, but they never carry the day. And 2,000 years later, people still think this is the way the universe was made or is constructed. So from Aristotle forward, the question, how old is the Earth, is not a question. The question, how old is the universe, it's not a question. So when did this question actually become a relevant question? Without knowing directly the answer to when or who, what do you have to do if you want to convince people that they should actually try to answer that question? What's that? Go down to the Grand Canyon? Well, you'll see lots of evidence, but geology really wasn't understood or invented till the end of the 18th century, so that's not going to help us quite yet. This is a more philosophical question.
Get the Earth out of the center of the universe.
Get the Earth out of the center of the universe. Aristotle says it's at the center of the universe, so what do you have to convince people of? If you want, discredit Aristotle. Yes, is that what you're going to say?
Well, I was just going to say, show that the circles aren't perfect circles.
Show the circles aren't perfect circles. I'm going to go with this answer. I mean, that's a corollary to the first answer, and that is you've got to discredit Aristotle. You've got to show that Aristotle's wrong. If Aristotle's physics is wrong, then this whole thing falls apart, and then this question becomes worth asking. That's hard to do. The person who pulled this off, Copernicus. Copernicus actually was not a very good astronomer, but he was a great mathematician. He only made about 8 observations in his entire life. Most of them were no good, and he didn't use them in his calculations. The observations that Copernicus used to do his work were from Ptolemy. They were from Hipparchus. They were from the Babylonians. They stretched back thousands of years. But there's nothing wrong with those observations. They're just not as accurate, perhaps, as modern observations. He looked at all that data, and he also was convinced or motivated by a deeper idea. Copernicus was very much a Neoplatonist, and for him that meant the sun must be the most important thing in the universe. The sun is the source of heat. The sun is the source of life for us. The sun clearly was a bigger object than the earth. The Greeks had figured that one out. So the sun ought to be the center of the universe. And that motivated Kepler to put the planets in orbit, if you will, around the sun rather than around the earth. Copernicus was also very much an Aristotelian, because in his model, the planets go around the sun in perfect circles. And in fact, it's not obvious that these are actual orbits for Copernicus. They're really spheres, Aristotelian spheres. And this little thing right here, that little circle is the circle of the moon going around the earth. You can think of that as being like an epicycle, except the moon goes around something, the earth, whereas normal epicycles go around nothing. But this pretty picture is what Copernicus described in chapter 1 of his book, published his book in 1543 on the revolutions of the celestial orbs. And in chapter 1 he said, the planets orbit the sun in perfect circular paths. But if you go into chapters 2 through 7, where the math is, the planets actually don't do that. They go on epicycles. He has 37 circles to make 6 objects go around the sun and make the data match the observations. But from a marketing standpoint, he said it's a heliocentric universe with the planets going in perfect circles around the sun. Mathematically, they didn't do that. And in fact, mathematically, the sun wasn't at the center. In his words, the sun is near the center. But this is the pretty picture of Copernicus. If Copernicus is right, and the sun is the center of the universe, then Aristotle's physics is wrong. Because Aristotle's physics say earth, air, fire, and water go down and up toward and away from the center of the universe. How in the world can this piece of earth go down toward the earth when the earth is not the center of the universe? How can these things go in perfect circles around something other than the earth when clearly the earth is the center of the universe, because stuff goes up and down toward the center of the universe, and obviously the stars look like they're going around the earth? Copernicus didn't win the day. He didn't publish his book in 1543 and have everybody say, Copernicus is great, Copernicus is right. In fact, he was widely ignored. By the end of the 16th century, there was one avowed Copernican in Europe, a guy named Michael Maslin. No other astronomer thought Copernicus was right. Now, Copernicus's mathematics was actually used to reform the calendar, the Gregorian calendar that fixed the calendar that was put in place in 1582. The church used Copernicus's mathematics, but they didn't accept his ideas, just his math, because his math was better. But when Copernicus does this, he changes the question. He raises the question, because in a heliocentric universe, the heavens are silent on the question, how old is the universe? Aristotle's physics are gone. You need some other method to figure out the age of the universe. But for the first time in 2,000 years, if you think Copernicus might be right, this question is actually a question you should ask, because we no longer know the answer. We don't know the age of the Earth. We don't know the age of the universe. So it's really 500 years ago that astronomers, physicists, theologians, philosophers began to ask this question, to think it was a valid question. Yes?
Could you comment a bit on the idea of finitude and boundaries for the universe?
Okay. How big is the universe? For Aristotelians, the universe was small. They thought they had proof that the universe is small based on a measurement called parallax. You can understand parallax by putting your finger in front of your eye. Go ahead. Embarrass yourself. Put your finger up. Shut one eye and look at your finger, and then shut the other eye and look at your finger. And what does your finger do? It moves. Give me a break. Your finger didn't move, but you observed it from a different place. You observed it from two locations 3.5 centimeters apart or something like that. Right? The Earth, if the Earth orbits the sun, then on July 1st, it's over there, and on January 1st, it's way over there. 93 million miles from the Earth to the sun, do it again, so you're 186 million miles apart. That's like your two eyes. And you're going to make observations not half a second apart, but 6 months apart. And you're going to look at the stars. And if you look at the stars, and if some of the stars are a little bit closer than other stars, then the stars that are close will appear to move. And to the ancient Greeks, they couldn't measure parallax. The stars did not move. Therefore, you could conclude from that that the stars are incredibly far away, and that's why you can't measure parallax. However, if you come to that conclusion, you're doing so because you've already decided the Earth orbits the sun. Aristotle didn't think the Earth orbits the sun. He thought the sun orbits the Earth. So on July 1st, you look up and you measure the positions of the stars. And on January 1st, you're still here. And you look up and you look at the positions of the stars, and they're not going to change because you haven't changed positions. Like you look at your finger with your right eye, and then you look at your finger with your right eye, and it's still where it was. So to Aristotle, there were two explanations for why the stars showed no parallax. One, the stars are incredibly far away, but his physics is invalid because all that stuff goes around the sun, including the Earth. Or his physics is right, and you can't measure parallax because the stars simply aren't very far away. Now, if the Earth doesn't move and the stars aren't very far away, you can test that further because you can go to one part of the Earth and make that same measurement and go to another part of the Earth and look at the stars, and you ought to see some parallax if the stars are close enough. But even doing that, you can't measure parallax. You can measure the parallax of the moon that way. Go to Sweden, go to Spain. You'll see if you could make simultaneous measurements, the moon would not be at exactly the same position relative to all the stars. Parallax. The moon shows parallax, the sun shows parallax. With modern telescopes, Mars shows parallax, Jupiter shows parallax. But to the ancient Greeks, without the telescopes, the sun and the moon did, but nothing else did. And that was evidence that the stars were at a certain distance, but not too far away, because if they were too far away, that was just a ridiculous universe. They just couldn't believe the universe could be that big. With Copernicus, the game changes, because with Copernicus, the Earth is orbiting the sun, and they still can't measure parallax. And if you can't measure parallax with a baseline on your triangle here of 186 million miles, the stars must be incredibly far away. So the universe got a lot bigger with Copernicus. To Aristotle, to medieval astronomers, the universe was small. The universe was understandable. And in a religious sense, heaven is just out there. It's almost within reach. That was psychologically the universe. It was comprehensible. With Copernicus, the universe becomes incredibly big to the point of being incomprehensibly big. If I tell you that the closest star is 4 light years away, that means nothing. If I then calculate that in kilometers, it's a really big number. None of us can actually understand what that means, and that's just the closest star. The universe is big, but it didn't used to be. The universe used to be a nice little place. Yes?
How could they keep time? I mean, these things involve, you can do things simultaneously.
Well, they couldn't. They weren't going to Sweden and Spain to make those simultaneous measurements. For the measurements of the size of the Earth with the stick in the ground, there are certain things you can coordinate because you know exactly when the sun crosses what's called your meridian. And if you are 100 miles exactly north of me, and we can figure out exactly what north is, then if you go 100 miles north of me, we know that when the sun crosses my meridian, it's crossing your meridian. And if we make the measurement at the same time that the sun's crossing the meridian, those are simultaneous observations. Short of something like that, it's hard to guarantee simultaneity. But most measurements that they were making didn't require that. Yes?
How did the Greeks deal with the, supposedly the Babylonians had records that showed that the summer solstice and the equinoxes had changed, the position of the stars, the dates in which they occurred, had changed over a period of time.
The first person who figured that out was Hipparchus. Oh, I'm sorry. The Babylonians had records that showed that the moment of the equinoxes changed with time, that the motion of the sun relative to the stars seemed to change. On March 21st this year, the sun won't be in exactly the same position relative to the stars as on March 21st last year. Aristotle didn't have those records. Aristarchus and Eratosthenes didn't have those records, but Hipparchus did, or he understood them well enough. And he figured out that there was this precession period that changes the seasons with respect to the calendrical year. He then had to add another motion to the sun. So the sun, instead of just having one motion of going around the earth in a perfect circle, there was a second motion that the sun had, which was a slow circular motion that took 26,000 years instead of 1 year. So it's 2 different motions. In the same way, if I'm the earth going around the sun, I have one motion going around, I have a second motion spinning. They're both circular motions. He added a second motion for the sun to make that work. He had to do the same thing for the moon to make the moon's orbit work. Yes?
We know the Earth's axis is tilted. How did Aristotle account for the seasons?
Aristotle didn't. Hipparchus did. He accounted for the seasons by taking the Earth and moving it away from the center. So imagine you have a circle for the sun. Let me go back to Aristotle. So we have here's the sun's circle around the Earth. And there's a distance from the sun's circle to the center. I'm going to move the center 1/24th of the distance toward the sun. So in that direction, the sun is at 23 units away from me, and in that direction, 6 months later, would be 25 units away from me. By doing that, the sun, as it comes through the sky, moves faster in part of the year and slower in part of the year. That violates Aristotle. But it allowed Hipparchus to predict the lengths of the seasons accurately. So now you ask the question, is Aristotle right or is Hipparchus right? Hipparchus' approach was to say, no, Aristotle's right, because otherwise we have no physics to explain anything. But this is just a mathematical solution that saves the appearances of Aristotle. I still have perfect circles. The Earth mathematically isn't at the center, but that's okay. But they could predict the lengths of the seasons accurately that way. And with the measurement of precession, they could predict the changes in the seasons, that the seasons, the first day of spring to us is always March 21st. But without a correct calendar, the first day of spring marches through the seasons. fairly, well, 10 minutes a year. So after a century, it's changed by a day. And after another century, 2 days. If you get your leap years right, you can keep the first day of spring on March 21st. But it took until 1582 to get that right. All right, back to Copernicus. I got 5 minutes left. Okay. All right, so after Copernicus shows up, we have this opportunity. We can think. And if you're going to think about what the answer to this question is, and it's 1600, you're going to use what resources you have. So let me quickly take you through a few things here. One of the great astronomers in history is Johannes Kepler. He said, I know how to figure this out. The Earth was created when the sun was at apogee, which means it's at the furthest point in its orbit. And when apogee occurs, when the sun is right here, in the head of the constellation Aries. There's no logic to it. But if you do that, you find that this occurred in 3993 BCE. Aha, you might say. Kepler was very religious, very mystical. He came up with this idea almost certainly because it gave him the answer he wanted to come up with. Okay? A colleague of his, another astronomer at the time, Christian Longomontanus, came up with the same answer. He used the same logic. The Earth was created when the sun is at apogee at the head of the constellation Aries. He got a different answer, 3964 BCE, but pretty close. That's comforting, pretty close. John Lightfoot comes along. John Lightfoot is a professor, a theologian. He was the vice chancellor at Cambridge University, and in 1642 he wrote this book, A Few Observations Upon the Book of Genesis. And he said man was created by the Trinity about the third hour of the day or 9 o'clock in the morning. And we're laughing, and that's okay. But in 1642, this was the pinnacle of scholarship. There was no other way to come up with the answer. If you want to come up with the answer of how old is the universe, and Aristotle's been thrown out, what are you going to do? Well, the Bible would seem to give you an opportunity to come up with an answer. So Biblical Chronology, which was actually born 1,500 years before this, had a good few decades. So he came up with this set of numbers. This is a chart from his book in which Seth was born 130 years after Adam. Enoch was born in year 235. Canaan in 325. The flood, where's the flood? Flood right here in year 1696. This is a who begat whom when chronology from Genesis. And it gave Lightfoot an answer of 4004 BCE. James Usher, who's the one you've almost certainly heard of, wrote a 4-volume compendium called the Annals from 1650 to 54. He was also a very distinguished scholar, professor and vice chancellor at Trinity College in Dublin, like Cambridge, one of the great universities in the world then and now. He was no slouch. There he is. His Annals came up with basically the same answer. So what does the Bible actually say? So here's what the Bible says. Or maybe this is what the Bible says. The Bible was either written in Hebrew or Greek or a mixture between Hebrew and Aramaic and Greek. You can choose. It was not written in the King's English. So if you're really going to do it right, you're going to consult these original sources, which in fact is what the scholars did. But for us, we can say, well, what does the King James Bible say? Because it's in English, and it says, in the beginning God created the heaven and the earth, which tells us that the heaven and the earth were created. This is the conflict with Aristotle. This is what was avoided for 1,500 years. But now Aristotle's gone, his ideas are debunked, so this is the only game in town. It says it was created. How do we figure out when it was created? Well, we look at the biblical sources, and this is our answer, and the answer is 4004 BCE, so the year of Usher was 1654. It had been 5,700 years since the creation. The Bible gives you a great answer. In the 17th century, this was a good answer. We're not in the 17th century, but when this was done, it was the pinnacle of scholarship. They were taking ancient Greek histories, ancient Jewish histories, ancient Latin histories, taken astronomical data, when did this eclipse occur relative to when this emperor ruled, and there is certainly some material in the Bible which appears to be historical, other material which may or may not be, but they treated it all as history, put it all together, and came up with this answer. And then Newton comes along, and Newton did the same deal. He took biblical events and he took eclipses and he put it together and said creation occurred in 3998 BCE. So we have this incredible result, and that is we have a scientific consensus. Right? Kepler and Newton and Longomontanus and Usher and Lightfoot all agree plus or minus 30 years. Obviously, we know the answer. There were problems at the time. If you look at the Greek Bible versus the Hebrew Bible, you have differences, for example, of whether Methuselah lived for 720 or 969 years. Okay. Whether we believe he lived for either of those isn't the question. There were issues because there were different versions of the Bible that caused scholarly debate at the end of the 17th century. And as soon as this consensus was developed, it fell apart. Which means the process is working. If the consensus isn't strong enough to survive scrutiny, then it's probably not right. So the game changed in the late 18th century with this guy, Leclerc, who, we're missing some words here, he came up with the brilliant idea that the Earth is cooling off. And you can measure it. The Earth is cooling off. If the Earth is cooling off, then it was hotter yesterday and hotter still the day before. And he said there's a limit to that. When the Earth gets hot enough, it would evaporate. And then the Earth isn't here. So I can create an upper limit on how old the Earth can be based on how hot the Earth could be. And he said that limit was 168,000 years. Which doesn't tell us the age of the Earth, but this is the beginning of a scientific effort, a real scientific effort to come up with an age for the Earth and for the universe. And I'm going to skip a couple slides because we really are out of time. But using radioactivity, we actually know the age of the Earth extremely well. There are meteorites with ages of 4,567,000,000 years. They're called carbonaceous chondrites. They're the oldest meteorites, and they all have the same age. The oldest moon rocks are between 4.4 and 4.5 billion years old. The only oldest intact sedimentary rocks are at 4 billion years old, and they're mineral grains, these little guys here called zircon grains. They're mineral grains inside the sedimentary rocks made of zircon. Zirconium makes the sheaths to those uranium rods in the reactors in Japan that are melting down, or maybe not melting down. Zirconium is really tough stuff. You know, cubic zirconium, the fake diamonds. It takes tremendous heat to melt this stuff. And in a normal sedimentary rock, when the rock erodes, the zircon grains don't erode. So you just have these little pebbles of zircon hanging around, and they wash into a stream, and they form into new rocks. And those oldest zircon grains all have ages between 4.3 and 4.4 billion years. It's pretty clear we know the age of the Earth. It's about 4.5 billion years old. That's the best we can do from here. In order to get an age for the universe, we can now go back to the very first question and say, the universe is older than the Earth. So the universe is at least 4.5 billion years old. How old is it? And that's where we'll go in the next 5 weeks. So thanks for being here. You stayed awake. I'm good.